Hello and welcome to this session in which we are going to solve problem 10.79, in which we have ambient conditions as 100 kilopascal and 300 Kelvin. Energy is supplied as 1200 kilojoule per kg air from a 1500 Kelvin source. So this thing is at 1500 Kelvin and the energy supplied is 1200 kilojoule per kg. And in some part of the process, a heat transfer loss, so the loss is 300 kilojoule per kg, and this happens at 750 Kelvin. The air leaves the engine at 100 kilopascal and 800 Kelvin. So we have to find out the first and the second law efficiencies. So because it's a loss, I'll write this as minus 300 kilojoule per kg. So if you write down the first law for a steady state steady flow process with all the heat transfers accounted for, we have 0 is equal to summation of q dot plus m dot air hi minus m dot air he minus w dot, where we have neglected the kinetic energy and potential energy changes as air passes from state 1 to state 2. If we divide by the mass of air, we have 0 equal to summation of q plus hi minus he minus w. This is equal to 0 equal to 1200 kilojoule per kg minus 300 kilojoule per kg plus hi minus he minus w. So this will yield the work done during the process. So the by definition of the first law efficiency, this is equal to the work obtained during the process by the amount of heat input to the process. So this should be divided by QH. So let's go to our computer and see what the calculation tells us. So we have QH equal to 1200, QL equal to minus 300. HI is the enthalpy of the inlet air. So because air is considered as an ideal gas, the enthalpy is simply a function of temperature, and in this case it's 300 Kelvin. Rather, if we make it in degrees Celsius, it's this. He is the enthalpy of air at T equal to 800. So then we write down the balance, the first law for the steady state steady flow process. So it's QH plus QL plus HI minus HE minus W, and eta I or eta 1 is equal to W by QH. So if you solve this, we obtain the first law efficiency as 0.3152. Now coming to the second law efficiency, the way to do it is that we first find out the reversible work, and then we compare the work obtained during this actual process against the benchmark of the reversible work. So how do we find the reversible work? We note from our studies that the irreversibility is defined as the W reversible minus W, which is nothing but T0 into Sgen. So if you write down the, so this is written in a per unit mass basis, so this should be small I. Rather, if I write it down as this, so it is W dot reversible minus W dot is equal to T0 S dot Gn. Okay, so how do we find the expression for T0 S dot Gen? So we have, for the steady state steady flow process, 0 is equal to summation of m dot I Si minus summation of m dot E Se minus summation of Qi by T0 Qi dot plus S dot Gn. If I divide by the mass flux, then I have simply Sgen is equal to summation of Q by T plus Se minus Si. In this case, this will be QH by TH plus QL by TL plus Se minus Si. So if I do T0 into Sgen, this will be simply multiplied by T0. So W reversible, if we look at this particular formula, this will be W actual plus T0 into Sgen. Where W actual, I mean, already we have it, but still, just to go through the derivation, W actual will be Hi minus He plus this should have been plus. So pardon me, that sign mistake was there. So this is all minus. It's a very, anyway. So minus QH by TH multiplied by T0 minus QL by TL divided by T0 plus QH minus QL plus T0 Se minus Si. And this gives us the classical formula that we have, which will be nothing but Hi minus T0 Si minus of He minus T0 Se plus QH 1 minus T0 by TH plus QL 1 minus T0 by TL and so on, where all the temperatures are obviously in Kelvin. However, with this expression in mind, let us go ahead and encode this into the computer. So for this, I now need to just work with this particular equation, because once T0 Sgen is known, I can simply add the W actual to find the W reversible. Okay, so the very first equation is W reversible is equal to W plus the irreversibility, where irreversibility is equal to T0 multiplied by Sgen, where T0 in this particular case, let us go and look into the problem. What is T0? It's 300 Kelvin. So T0 is 300. We need all the temperatures in Kelvin now. So now let us write down the expression for Sgen. So 0 is equal to Si minus Se plus QH by TH minus rather plus QL by TL. So for those of you who are wondering how I have written a positive sign despite Q being a loss, the fact is I have accounted for the negative sign already in this expression, so I don't need to account for a negative sign over here. The sign is already conveyed. Okay, so this expression will give me Sgen. However, TH and TL have to be defined. So TH is 1500 Kelvin, TL is 750 Kelvin. Si is the entropy of air at T equal to the given conditions, and P equal to 100 kPa. Se is the entropy of air at T equal to the given temperature at exit and the given pressure at exit. So the given pressure is also both the pressures are at atmospheric pressure. So the inlet and the exit of the heat engine are at 100 kilopascal. So that gives us the entropy at the inlet and the exit. Unlike the enthalpy, the entropy is a function of both pressure and temperature, as you might have seen in the theory class. So with this, we should now be able to obtain Sgen. Let's see. Yes, we do have Sgen. So then we also have the irreversibility and W reversible. So the eta second law should now be equal to W by W reversible. Let's see what the value is. It comes out to be 0.6719. So essentially, of the possible 562.9 kilojoule per kg, one is able to only make use of the 378.2 kilojoule per kg, implying that you are only able to use 67.2% of the total work that you could have hypothetically obtained if you were to convert all the processes into a reversible process, implying the Sgen of the total cycle should be 0. So the derivation and the problem should make the ideas of the first law and second law efficiency very clear. And with this note, I end this video. I will see you next time.